Hi, Ricardo here with Math Matters, part of the Golden Ratio series. Today we're going to talk about the Fibonacci sequence. So, we're going to talk about the Fibonacci sequence, why this relates to the Golden Ratio, how that relates to the nature around us, and how we can get from this sequence to the number phi. So, a Fibonacci sequence. Well, the word sequence means a list of numbers. And usually a sequence isn't a random list of numbers that I say off the top of my head. They always have a pattern to it. So, the Fibonacci sequence has a very particular pattern where instead of adding 1 like you would when you just count numbers, instead of just 0, 1, 2, 3, 4, the first two terms are defined as 0 and 1, but then every other term is the sum of the previous two. So that's why the first two are defined, because you need somewhere to start with, right? So the third term is the sum of these two. 0 plus 1, which is 1. Then the fourth is 1 plus 1, 2. Next is 2 plus 1, 3. And then 2 plus 3, 5. 5 plus 3, 8. 8 plus 15, 13. 8 plus 13, 21. And, for good measure, 13 plus 21, 34. Okay? Well, the reason I say for good measure is because there's a very interesting fact that comes up with the Fibonacci sequence. And it turns out that the Fibonacci sequence, which obviously increases by different numbers every time, instead of just adding 1, you're adding a new unique number, right? So it's not just as easy as just counting, right? You have to write them all out one by one. And it increases by a different amount, but the ratio it increases by is always the same. And believe it or not, the ratio it increases by is the golden ratio. So we take one term divided by the first term, divided by the previous term to find its ratio, right? So 34 divided by 21 is the ratio of how much it's increased, because that's a ratio greater than 1, and it's how much it's increased. You may say 2 over 1 is 2. That's not a very good approximation of the golden ratio, 1.6. But as these numbers get bigger and bigger, it gets closer and closer to the golden ratio, and these numbers get very large very soon, and eventually it's nearly exactly the golden ratio. And this isn't a coincidence. It has a lot to do with the way the golden ratio can divide a segment, right, in this particular manner, and how each term depends on the divisions. So if I had a segment of 34 and I divided it in 13 and 21, all terms have to follow the golden ratio. So let's prove that real quick. Let's take 21 and 13. So 21 divided by 13, I'm arguing, is close to the golden ratio. And if you take out your calculator, you'll find out 21 divided by 13 is in fact 1.615. Very good approximation. I mean, better than my torso was divided in the golden ratio in my other video. But it's about, 0.003. 3 1,000ths off the golden ratio. Not bad. It turns out that these two terms, 34 and 21, are even closer. 34 divided by 21, again, take out your calculators, is 1.619. So 1 1,000th higher than the golden ratio. And as these numbers get bigger and bigger, the ratio gets closer and closer to this golden ratio, or phi. And that's a very interesting concept because the Fibonacci sequence is also seen throughout nature. And the way we prove that is through the golden spiral. All I did here is redraw the Fibonacci sequence in a more geometrical sense. So, by drawing squares that have side lengths that are the Fibonacci sequence terms, we can bring this Fibonacci sequence and the golden ratio into geometry and therefore into nature. So, I drew side lengths of the squares that are the Fibonacci terms. So 1 and 1 are all the side lengths of these first two squares. And because they're connected and they make up one side of the new square, 1 plus 1, which are the side lengths, equals 2. And that's one of the side lengths, and therefore all of the side lengths of my new square, which is then 2 by 2 by 2 by 2. And then 1 plus 2 makes the new side of the next square, which is 3. And then 2 plus 3, 2 and 3, make the side length of the new square, which is 5. So this addition is represented both by this formula and by the geometry here. And I only went up to 13 because the numbers get very large, right? 21 would be up here, 34 would be that way, and it just gets bigger and bigger. So you may argue, Ricardo, how did you know to draw them in this order? Could you have flipped it? I could have flipped it, But the one important thing to draw about the Fibonacci sequence is that the first two have to be on top of each other so that they make the next square, or they can be side by side, but then it's flipped, everything's flipped, as long as every square is touching the next term. So 1 and 1 touch 2. So if I start at 1 and 1, I can draw what's called the Fibonacci spiral or the golden spiral, using the diagonals and drawing a nice spiral like that. So let's try, see if I can do this reasonably well. Something like that. So this spiral is seen throughout nature. It may look familiar to you if you've seen seashells, so the inside of seashells, or the inside of hermit crabs. All kinds of different shells follow this very directly. However, it's more prevalent than just in shells. It's in sunflowers, sunflower seeds. Most plants actually have leaf arrangements that follow this. Pine cones have spirals that follow this. Pineapples also have spirals that follow this and the Fibonacci sequence. And we'll see how we can connect that directly. Hi guys, thank you so much for watching my video. It really does mean a lot. And if you enjoyed this one, I encourage you to watch the next video of my series. And hey, if you're done with the series, there's always more mathematics to learn. Because remember, math matters.